Hi everyone, this is Mrs. Jade. Today we're going to be doing rational equation word problems, but first please pause the video and give this warm up a try. Alright, go ahead and check your work here. So remember, when you're solving a rational equation, we first list our restrictions, we list our LCD, and then we multiply both sides of our equation by the LCD, which clears our fractions. And as long as your solution is not your domain restriction, you should be good to go. For part B, this one we're going to use a different strategy. We're still going to start by listing our restrictions, but when you have a single rational expression equal to a single rational expression, you can solve this one simply by cross multiplying. However, multiplying both sides by the LCD would work as well. Today we are going to be solving rational equation word problems, which will require us to set up a rational equation and solve it. So I think the harder thing that we're going to do today is setting up the equation. So once we have that created, the solving part should be a piece of cake for us. So there's two main types of word problems we're going to do today. One I call a work word problem. So if you look at this first example, it says Lisa can paint a room in 5 hours. Her sister Laura can paint the same room in 8 hours. How long would it take the sisters to paint the room together? So as with any word problem, the first thing we're always going to do is define a variable. If it asks how long would it take the sisters to paint the room together, the variable should answer that question. So we'll say x equals hours when working together. So for these types of problems, I like to set up my equation by thinking about how much of the job can they complete in 1 hour. So in 1 hour, well, let's start by talking about Lisa. So if Lisa takes 5 hours to paint the room, in 1 hour, she has finished 1/5 of the job. 1/5 of the job is done. And then Laura, well, it takes Laura 8 hours. So in 1 hour, she has finished 1/8 of a job. And if you add those up, it should equal the amount of time or the amount of the job that they've finished working together. So if it takes them X hours working together, in 1 hour, they've finished 1/X of the job. So that's how I always set up these types of problems. And then all we have to do from here is solve. So we have a pretty simple rational equation. We see that x cannot equal 0, which wouldn't make sense anyways, right? Obviously, it wouldn't take them 0 hours to complete the job. And then I'm going to look for an LCD. So I can see here that my LCD is 40x. So I'm going to multiply both sides of my equation by 40x. And when I do that, I'm multiplying every single term, and it goes to the numerator. So let's see what we have left here. 40 divided by 5 is 8, so I have 8x. 40 divided by 8 is 5, plus 5x equals, here the x's cancel out, and I'm just left with 40. So then I just need to finish solving. So I have 13x equals 40. So x equals 40/13. Now here, this is a word problem. So if you just told someone, hey, it takes them 40/13 hours, like they're going to look at you like, huh, what does that mean? Is there a better way you could tell me this answer? So this would be one where it'd be good to get a decimal approximation here. So we get 3.08 if I round to the nearest hundreds. So let's say, we'll say about 3 hours will be our final answer. And again, I might ask you to round in a specific way, or I might not. So this one is pretty close to 3 hours, so we'll just say it takes them about 3 hours when working together. And then we should, use some logic here. If it takes Lisa 5 hours and it takes Laura 8 hours, when they're working together, it should take them less time than any of the individual amounts of time. All right, let's try one more together. Here it says Catherine can clean up her toys in 9 minutes. When Rosemary and Catherine work together, they can clean up their toys in just 5 minutes. How long, I'm going to highlight it because this is the question, how long would it take Rosemary to clean up the toys by herself? So let's define our variable in a way that answers the question. Would be the minutes it takes Rosemary alone. Now from here, I'm still going to set this up in the same way. I'm going to think about, okay, in 1 hour, how much of the job did Catherine do? And in 1 hour, how much of the job did Rosemary do? And then that should equal how much of the job they've done together. So again, it takes Catherine 9 minutes. So sorry, and we're not going to think about it in terms of in 1 hour. We'll think of it in terms of in 1 minute. So in 1 minute, she's finished 1/9 of the job. Now for Rosemary, it takes her X minutes. So in 1 minute, she's finished 1/x of the job. And together, it takes them 5 minutes. So in 1 minute, they have finished 1/5 of the job. So it's the same setup as the last example, but you'll notice here the variable represents one of the girls working alone. So sometimes the variable will be how long it takes when they're working together, or it could be one of the individual time lengths. So here, again, we see that x cannot equal 0, and we see that our LCD is 45x. So every single term gets multiplied by 45x. And again, I'm not doing this to the numerator and the denominator. I'm doing it to the left and right sides of the equation. So this leaves me with 5x, and then here the x's cancel out. So plus 45 equals 9x. And then we'll move the common terms to the same side. And I will divide by 4. So you could leave your answer like that. That's fine. But again, usually it's better to think of, to answer a real life word problem with a decimal. It's just a little easier for most people to understand. So we can say it takes Rosemary 11.25 minutes. And of course, if you wanted to, you could say 11 minutes and 15 seconds if you'd like. Of course, that means the same thing as 11.25 minutes. Just make sure that this time we are in minutes, not hours. A really good thing to do is go back and look at how you define your variables. So we clearly define x as the minutes it takes Rosemary working alone. All right, the other really common type of rational equation word problems we see, I call them distance rate time word problems. So let's take a look here. This says Jenna and Katie plan to meet at Saratoga Bagels on Saturday morning. They both leave their houses at the same time and arrive at the same time. So they leave at the same time and arrive at the same time. So when I see that, it just means they were driving or walking, turns out driving, for the same amount of time. If they start and leave at the same time, they are driving for the same time. And it says, even though Katie lives 5 miles away and Jenna lives 8 miles away. If Jenna was driving 2 miles per hour faster than Katie, how fast was Jenna driving? So again, just like in the last examples, I look for the question, which is how fast was Jenna driving, and that's how I'm going to define my variable. X equals the speed in miles per hour of Jenna. So it's really important when you're defining your variable to be specific and to include units. So it's the speed in miles per hour of Jenna. So looking at this, I can also make a statement, a mathematical statement using this. Jenna was driving 2 miles per hour faster than Katie. So that means that if I take Jenna's speed and I subtract 2, that would be the speed in miles per hour of Katie, right? Because again, if Jenna is driving faster, Katie should be driving slower. So now we found a way to actually define the speed of both Jenna and Katie. So now we're going to have to look at our classic distance equals rate times time formula. So when I, again, look back here, the one thing that is constant between the two of them is the time, right? Because they both leave and arrive at the same time. We know that the time is the same. So if I isolate t in this equation, I get t equals d over r. I know that the time it takes Katie should equal the time it takes Jenna. And then, so t equals t. And so that means distance divided by rate should equal distance divided by rate, because time is distance over rate. And these are two things that we know that we are given or can define. So if we look at the distance that Katie traveled, it says that Katie lives 5 miles away. So Katie's distance is 5, and her rate we defined as x minus 2. And then Jenna, it says Jenna lives 8 miles away, so that's her distance, and we defined her rate or speed as x. And now we have our rational equation. And just like in the warm-up, this is one where we have a single rational expression equal to a single rational expression, so we can cross multiply to solve this. First, I am going to list my restrictions. Okay, so I'm going to cross multiply. So 5 times x equals 8 times x minus 2. We have a pretty simple linear equation here. So we have 3x equals 16. I subtracted 5x from both sides and added 16 to both sides. So x equals 16 over 3, which is about 5.3. And remember what x represents. It represents the speed in Jenna in miles per hour. So we'll say x equals 5.3 miles per hour. So that is the rate at which Jenna is driving. All right, let's try one more together. So this says Mrs. J is rowing in a river. She can row 15 miles going downstream in the same time that she can row 5 miles going upstream. So let's talk about this for 1 second. Why is it that she can row 15 miles going downstream in the same time that she can only row 4 miles going upstream, right? Well, here's a river, right? So if the current is going in this direction, right, this would be considered downstream. So downstream is going in this direction. And when you're going downstream, you're going with the current. So the current is actually pushing you along and increasing your speed. Now, when you're going this direction would be upstream. So when you're going upstream, you're actually fighting against the current. So the current is actually slowing you down. So that's why when you're going downstream, you can travel farther in the same amount of time as when you're going upstream. So this says, if the speed of the current is 5 miles per hour, how fast is Mrs. G.A. rowing in still water, meaning without the current included? So I'm going to define x as the speed in miles per hour of Mrs. G.A. Okay, so if the speed of the current is 5 miles per hour, well, that means when we're going downstream, that current, again, is pushing us and is actually increasing the speed. So you have the speed without the current, which we called x, plus the speed of the current. So the overall speed moving downstream would actually be x plus 5 miles per hour. Okay, so you do the speed of the vessel in still water plus the speed of the current. It's actually making your speed faster. But if we're going upstream, then Mrs. GA would be traveling x minus 5 miles per hour. It's the speed of the vessel and then minus the speed of the current because it's physically pushing you in the direction that you don't want to be going. So you can see that the overall speed is a combination of the speed that Mrs. GA is rowing plus or minus the speed of the current. So here's the upstream speed and here's the downstream speed. So this is another one where it said that they were, it's in the same amount of time. So I'm going to go back to the time equals distance over rate. So that means that the time, and it did say in the same time. So the time downstream should equal the time upstream. So again, if t equals t, then the distance over rate should equal the distance over rate. Now all we have to do is fill in those variables. So the distance going downstream, it says, is 15 miles. And we know that the rate going downstream we defined as x plus 5. And then if we look back at the problem, it says the distance going downstream is, upstream is 4 miles. So 4 is that distance. And the rate going upstream is x minus 5. So from here, we have our equation, and all we need to do is solve. So I'm going to cross multiply, and again, I see that x can't equal negative 5, which wouldn't make sense anyways because it's a speed, or positive 5. I'm going to cross multiply. And then we have another rational equation here. We're going to set our equation, we'll move all of our x terms to the same side, and then I'm going to add 75 to both sides. And I'm going to get a decimal approximation for this. So we'll say about, I'll round to the nearest tens for this one, 8.6. And again, what was x? Well, x was the speed of Mrs. GA, and again, that's in still water, so not including the current. So 8.6 miles per hour is how fast Mrs. GA can row up or down the river. And again, that is in still water, so when we see that phrase, it means not including the current. So if you wanted to know how fast was she going when she was moving downstream, you would just add 5 to that. If you want to know her overall rate when she's going upstream, you would just subtract 5. All right, so those are the two main types of rational equation word problems you need to be comfortable with: the work word problems and then the distance equals rate times time word problems. All right, that is all for today's video. Thank you so much for watching.